This is where we have our Boolean equation. And we now want to convert this one to a Boolean, a combinational circuit. So first of all, let's look at the signals that we need in the input. We need two signals, which is A and B. But we can see that it's not only A and B. We still have the two versions of A, then two versions of B. For the two versions of A, we have A bar, then we have A. So assuming I have an electronic signal, which is A here, I can separate it into two. Then one part of it, I invert it. Why do I put this NOT gate here? This is because when I do this, I'll be able to achieve the inversion of A. But the other side of it, I leave it to be straight. So this one will give me my A bar, then this one will give me the A. Same thing applies to our B. So let's do the same thing for B. We take this part through a NOT gate, then I have my B bar, then this side will be our B. So this is how we are going to get the signals, or the four different signals for our inputs. Now we watch the whole Boolean equation. You can see that A bar B is combined using an AND gate because they are multiplied. This is also an AND gate, this is also an AND gate. So we have three AND gates to be taking the inputs. So I'll lay my AND gates here. There are three. So let's look at the first AND gate. It takes A bar B. Where is our A bar? A bar is here. We connect it. Then we have B. We connect that one too. Because we know that the first one is taking A bar B. In the same way, let's check the second AND gate. That is A B bar. Where is my A? A is here. Then I have my B bar also here. But there is something you have to check in electronics. When you are drawing schematic diagrams like this, we don't do this. We don't do this in electronics. What you do is that, let's see, the first line was like this. If the second line is crossing, you jump like this so that it becomes neat. So we get here, we jump like this, then we have it. Now let's go to the last one, which is AB. So we can pick our A from here to this, then we pick our B from here to this. Now I've been able to connect all my three AND gates. But remember, all these AND gates are combined by an OR gate, which is plus. So what do? I can choose to put all of them into a 3-input OR gate, or two input what? OR gates. All these are good for the solution. So what I'll do is that I'll use the two. So when I have one 2-input OR gate like this, I can use that one to combine this and this. Then I have my output coming like this. Then the outputs, I can now combine this output with this. So it's simple. It's just like I have 5 plus 8, or let me say I have 5 plus 3 plus 2. Plus 2. I can choose to work this and get 8 before adding it to this to get my what? 10. It's the same way. Or I can choose to type them straight away and get my answer. So we are doing this systematically. So therefore, I can now have my OR gate like this. So let's take this one off. I have my OR gate like this. Then I connect this. Then I connect this one too. Then I have my output as what? The Y. So finally, this is the what? The combinational circuit that will be used to implement the table that we had as the solution to the problem statement that we started with. Now, let's continue. With this, we know that when we simulate this in our software, we should be able to get the answers. Example of the software that you can use is Proteus IS. If I simulate this, I should be able to get the table, or I should be able to verify the table for whatever that we had. Now, we continue with this. We have to do what is called optimization. What do I mean by optimization? When you go to the market, you will be able to get two versions of electronic devices. Maybe device 1, device 2. You see them to be having the same logo. They will all be claiming that they are all from the same factory, but sometimes it's not so. So people say that maybe device 1 is original, then device 2 is fake. I don't like calling an electronic device a fake device. Why? Because there were efforts that were made in each of them. The only difference is that one of them was able to go further, to do a lot of optimizations to satisfy the customer needs, unlike the other type. So in there, we don't say a fake device. In electronics, the best thing to use is to use low grade, but not fake, because they are all achieving the aim. Now, so let's do what is called optimization to this. But first of all, let's look at something. Let's do some analysis to see. We are going to analyze about four parameters. The first one is, let's talk of weights. If I talk of the weight of this device, let's say one gate is giving us maybe, let's say one gate is weighing 2 kilograms or 2 grams. Then I have 1, 2, 3, 4, 5, 6, 7. It tells you that I'm going to have 7 grams. But then in reality, we don't do this. When we go deeper into VLSI, we can see that the IC that will be able to give us an AND gate always contain something like maybe 4 of these on one IC. So if one IC is having a weight of maybe, let me say 1 gram. I think I made a mistake here. Let's say one of them is 2 grams. Then finally, what we were able to talk about is that 2 multiplied by 7 will rather give us 14 grams. Okay, so we'll not go to the main idea of the IC yet. We'll go to that when I finish with the whole thing. Now, so it tells you that this whole thing will be weighing 14 grams. Now let's go to something called volume. Volume of the device that we are going to design. Assuming one device is giving me maybe 3 millimeter cube. At the end of the day, if I multiply this by 1, 2, 3, 4, 5, 6, 7, it tells you that we are going to have 21 millimeter cube. Then we talk of something like power consumption. You see that the electronic device will be consuming power. If each gate is going to consume about maybe 2 watts, it tells you that we are going to have 14 watts. The same way we talk of speed. So whenever you are dealing with these kind of combinational circuits, when you propagate a signal from one point to the end, it tells you that at each gate we are going to have a delay of signal. So assuming each signal is being delayed, or each gate is delaying the signal by maybe 0.5 seconds, it tells you that with a 7 we are going to have 3.5 seconds in total delay. So with this analysis, we can now go to the optimization. Then after that, we compare. So let's see the optimization. Why do we optimize? We try to reduce the size, we try to reduce the weight, the power consumption, and the speed, or the delay, the speed delay. So at that point, we are rather increasing the speed. But then what we are doing is that at the end of the day, the optimized version that we had, should we compromise the performance? No. We are not compromising, because at the end of the day, when you simulate these two circuits, they should all be able to perform the same way. So if you use the truth table to verify, this design and the design that we are going to have as the optimal design should all perform equally. So let's see, we start with our Boolean equation. A bar B plus AB bar plus what? AB. Let's start solving. We all know that we can do some kind of simplification here, or factorization. I see A here, I see A here. So definitely I can say A bar B plus A out, I have B bar plus what? B. But in digital electronics or in Boolean rules, one of the rules tells us that this one will give us 1. So finally, I can have y to be equal to a by b plus what? A. We meet another rule, which also tells us that if I have k plus k bar multiplied by anything like gamma, then this one becomes insignificant. So the whole thing becomes k plus gamma. In the same vein, if I'm having k bar plus k multiplied by gamma, it tells you that since this is the image of this one becomes insignificant. So it becomes k bar plus gamma. As simple as that. So we are going to apply such a rule here. When I look at the final statement, it tells us that A is the image of A bar or the inversion of A bar. But you see A standing alone here and its inversion standing with us. It tells you that this A bar is insignificant. So y will now be equal to b plus a, which is the same as y to be equal to a plus b. So when you look at this critically, you can see that this one can just be implemented using an OR gate. So therefore, if I have my signals as A, I have another signal as B, I can just implement the whole thing by using an OR gate. So finally, I have this just one gate implementing this, and I'll be able to achieve the same solution as the whole of this big combinational circuit. So now, let's quickly analyze this against the circuit. If you look at the whole thing, it looks like, or it is clear, that weight has drastically reduced. Because we are saying that if one gate is 2 grams, then definitely, since we are using one, this one will be 2 grams as compared to 14 grams in this design. When we talk of volume, if it is 3 millimeter cube, then this one becomes 3 millimeter cube as compared to 21 millimeter cube. We talk of power consumption. If it is 2 watts, then this one will be consuming 2 watts as compared to 14 watts here. We talk of speed, or we talk of delay. Since this one is having only one gate, it will only be delaying by 0.5 as compared to 3.5 seconds delay here. So definitely, this design is now an optimal design that will be a little bit or more faster than this design. So that one will be having more speed than this. So finally, this is where we will come to with this kind of simple solution that we are going to implement to solve the problem with the intrusion system. So what happens is that when you get to the industry with this kind of design or this, the engineers can now base on that to write a hardware development language. Precisely, we call it VHDL. That is very large scale integration hardware development language. It's a special language that we use so that we use it to program combinational circuits like this, upload it onto a robot, then the robot will base on whatever that we wrote and cut the chips for us, or it will be able to cut the electronic boards for us. But I always advise students that please, when you are learning some of these things, you should be careful. Why? Because if it is software that you are designing, by making a mistake in the software, it's easier to go and correct the software and update. But with this kind of hardware, at the end of the day, the robot is going to cut the board, which is just rigid, and there's nothing you can do with it, or there's nothing that you can do about it when you make mistake. So we are dealing with something like this, you should be very careful. Simulate it, verify all your tables, and make sure everything is in line before you now implement the robotic fabrication. So thank you. This is where I'll bring you to. We meet for the next video. Thank you.